Welcome to the fourth video of Module 4, where we're going to look at applications of exponential growth and decay. In example 2, we have an example of exponential growth. It says a biologist finds that bacteria grow in a petri dish at a rate of 1.8% each hour. A culture was started with 750 cells, so growth can be expressed by the equation n is equal to 750 times 1.018 to the power of t. Part A asks approximately how many bacteria are present after 20 hours. What we are looking for is to find n for t is equal to 20 hours. So t is equal to 20. Subbing this into our original equation, we have n is equal to 750 times 1.018 to the power of 20. Now we can evaluate this on our calculator, and we find that there are 1,071.56 bacteria present after 20 hours. Therefore, approximately 1,072 bacteria are present after the 20-hour period. Part B asks at approximately what time would there be 4,500 bacteria in the petri dish, and we want to round our final answer to 1 decimal place. This question works out to looking for the value of t when we will have 4,500 bacteria. Subbing our values into the original equation, we get 4,500 is equal to 750 times 1.018 to the power of t. The first step is to isolate for b to the power of t, which is 1.018 to the power of t. To do so, we divide both sides of the equation by our initial number of bacteria, so 750. And we see that on the right-hand side of the equation, the 750 cancels out. This simplifies to 6 is equal to 1.018 to the power of t. Now for step 2, we write our existing equation in log form, and we get that t is equal to log base 1.018 of 6. Now since our calculator can only evaluate log with base 10, we use the change of base formula. We get log of 6 divided by log of 1.018, which works out to be approximately 100. We will round our final answer to 1 decimal place, so we find that there will be approximately 4,500 bacteria present after approximately 100.4 hours. So now that we've looked at an example of exponential growth and decay, I want you to pause the video and practice the following questions. Practice question number 1 says the number of bacteria present in a culture n at time t in hours is given by the equation n is equal to 3,000 times 2 to the power of t. Part A asks what is the initial population. The initial population is 3,000 bacteria. We can determine this just from looking at the a value in our equation or by substituting the value of t equal to 0 and solving for n. Part B asks how long will it take the population to triple in size, and we want to round our final answer to 1 decimal place. Tripling in size requires that n is equal to 3 times what was initially there. So 3 times 3,000, which is 9,000 bacteria present, and we want to find t for that to happen. If we substitute 9,000 into the original equation, we get 9,000 is equal to 3,000 times 2 to the power of t. Recall that step 1 is to solve for 2 to the power of t, so isolate it by dividing both sides of the equation by our a value. And we get that 3 is equal to 2 to the power of t. Expressing this exponential equation in logarithmic form, we get t is equal to log base 2 of 3. Evaluate t, get log base 10 of 3 divided by log of our base 2, which is equal to 1.6 hours if we round to 1 decimal place. Example 2 says the amount of cobalt-60 in grams in a storage facility at time t is given by the equation C is equal to 200 times 0.88 to the power of t, where time is measured in years. Part A says how much cobalt-60 was initially present. From the equation, we see that there were 200 grams initially present. Part B asks us to find the half-life of the sample of cobalt-60. If we initially have 200 grams present, we want the amount of time to when there's half of that amount present. So we want to find the value of t when C is equal to 100 grams. Dividing both sides of the equation by our A value, we get that 0.5 is equal to 0.88 to the power of t. Therefore, t is equal to log of base 0.88 of 0.5, the logarithmic form of the exponential equation. Therefore, log 0.5 divided by log of 0.88 will give us a value of t of 5 years when rounded to the nearest whole year. Therefore, the half-life of cobalt-60 is approximately 5 years. Question number 3 is another exponential decay problem. It says, the amount of cobalt-60 in grams in a storage facility at time t is given by C is equal to 400 times 0.88 to the power of t. And part A asks how much cobalt-60 was initially present. We know that we initially had 400 grams. Part B says, what is the half-life of the sample of cobalt-60? So that works out to wanting to find the value of t when C is equal to 200 grams. Solving for t, we find that t is approximately equal to 5 years. This is the same half-life as we found in part 2b. Question 4 says, what do you notice about the answers from question 2 and 3, and what does this suggest to us about half-life of radioactive material? We observed that the half-life was the same in question 2 and 3, and that the initial value for the amount of cobalt-60 present does not affect the half-life. Good job on all these application problems with exponential growth and decay. In the 5th and final video of Module 4, we'll be looking at pH application problems involving logarithmic equations and solving them for various questions.